Okay, welcome back everyone. So we are finally rolling on into section 3.3, which is going to be, it's a very long section. So of course it has a corresponding title, Increasing and Decreasing Functions and the First Derivative Test. Doesn't that sound good? So we will get to that in just a little bit. But first, as always, we're going to do the homework that we had from the end of the last video. And so that one was over Rolle's theorem and the mean value theorem. So we will start with that. So here we go. Right off the bat, let's do number 12. Number 12 was f of x equals x squared minus 8x plus 5. And then it had an interval from 2 to 6. Now, this was the instructions for this problem were to use Rolle's theorem to find a value on this interval that had a slope of 0. So that's kind of a backwards way of looking at it, but okay. Typically, what you would do is you would have two values. In this case, we're just going to look at the endpoints. I think they've arranged it to where it will work out. And if those endpoints wind up having the same y value, so I'll erase this in just a little bit for right now, describe Rolle's theorem one more time. Say I have a function, I don't know, something that looks like this maybe. And I have two locations that have the exact same y value. We'll call this A and this one B. So if they have the same y value, Rolle's theorem, and it's a continuous function, you have to have that. Rolle's theorem guarantees that in at least one location, you have a slope of 0 because it's impossible to get from point A to point B without having at least one min, max, something like that. So in this case, it turns out there were two, but all Rolle's theorem does is it guarantees there's at least one. So, and of course, this graph does not correspond to what's above. This is just an example of what Rolle's theorem said. So let me erase that. I'm going to have to increase the size of my eraser to be able to get this off fairly smoothly. I need to make it bigger. It's just not going to cut it. There we go. So let's get it back down to a manageable size before I try to erase something again and wipe out half of what's on the screen. Alrighty, so first thing we want to do is check these endpoints out, see what we get. So let's see, f of 2 equals, well, it's going to give us 2 squared minus 8 times 2 plus 5. So 2 squared is 4, plus 5 is 9, minus 16, that gives me a negative 7. Alrighty, now I'm going to look at 6. F of 6 equals, well, 6 squared minus 8 times 6 plus 5. Whoop, I don't know where that one came from. There's no print there. Equals, well, 36 plus 5 is 41 minus 48. Again, we get negative 7. Now, these two y values are exactly the same. So Rolle's theorem guarantees there is at least one point between 2 and 6, x equals 2 and x equals 6, where the slope is 0. So how do we find that? Well, first off, we set the slope, and we find the first derivative of the function. We go f prime of x equals, well, that's going to give us 2x minus 8. Now I'm going to set the first derivative equal to 0, so f prime of x equals 0 means 2x minus 8 equals 0, and this is going to give us that x equals 4 when the dust settles. Okay, now notice that x equals 4 is between x equals 2, x equals 6, so 6, so we have confirmation that Rolle's theorem worked. So I'm happy if you just do something like this. You can solve for the value and then just point that it's between the interval. But if you wanted to say it in actual language, you could say that since x equals 2 and x equals 6, had the same y value and the function was continuous, then Rolle's theorem said that there was at least one point in between x equals 2 and x equals 6 that had a slope of 0. And what do you know? We just confirmed that when we found that x equals 4 occurs at, has a slope of 0. So kind of cool. So that's the first one, knocked out, not too bad. We can move on now to the second one. So let me clear the screen. Okay, so next we have 17, and 17 was f of x is equal to x squared minus 2x minus 3 over x plus 2, and the interval was from -1 to 3. Now I have a slight worry here, something to at least watch out for, that since this is a rational expression and it's a fraction, and there is a way for the denominator to go to 0, which is going to wind up causing a discontinuity. But the discontinuity is going to occur at x equals -2. But since x equals -2 is outside of the interval we're looking at, we don't care. The interval that we're looking at is completely continuous from -1 to 3. This function, totally fine. So we're good to go with it. First thing we're going to do is we're going to plug in our two values and see if magically the y values match. So let's just see what we get. Let's try f of -1. So f of -1 is going to be -1 squared is 1 plus 2 minus 3. It's going to give me a 0. And then f of 3, oh, I don't care what the bottom is as long as it's not a 0 as well, and -1 plus 2 is +1. The top went to 0, the bottom wasn't 0, so the overall function's value was 0. So 0 over anything that's not 0 or an infinity is 0. So next thing we do is plug in 3, so we get 3 squared minus 6 minus 3. Well, that is also 0. What do you know? So since they have the exact same y value, Rolle's theorem guarantees there's at least one point in between x equals -1 and x equals -3 that has a slope of 0. So how do we find that? Well, we take the derivative. So f prime of x is going to be, and here's where it gets interesting because this is a quotient. So we've got at the bottom x plus 2 times derivative of the top, 2x minus 2 minus the top, x squared minus 2x minus 3 times derivative of the bottom, 1, and all of that over the bottom squared, x plus 2 quantity squared. Okay, so I'm going to distribute all this and so I can collect like terms. So I'll get f prime of x rather is equal to, here we go, 2x squared minus 2x plus 4x minus 4, and then distribute this negative sign here, minus x squared plus 2x plus 3. And all of that is going to be over x plus 2 quantity squared. Alrighty, so I'm going to condense that a little bit and get 2x squared minus x squared is going to be x squared. Negative 2x plus 4x is positive 2x plus 2x again is 4x. And then negative 4 plus 3 is -1. And that is over x plus 2 quantity squared. That is our first derivative. Okay, so I'm going to need to go to the next page, but I'm going to set that equal to 0. So let me clear this. And then we will set that equal to 0. So I've got f prime of x is equal to x squared plus 4x minus 1 and over x plus 2 quantity squared. Now when I set that equal to 0 and solve, I need to be a little bit careful because this would be a jumbled mess if I tried to solve this as is. So instead I'm going to use what I just talked about a little bit ago, that anytime I have a fraction equal to 0, that means the top was equal to 0. So if I can make just the top go to 0, the whole thing is equal to 0. So I'm going to set x squared plus 4x minus 1 equal to 0. And at this point, I can't factor that. That isn't one of the nice little pairs of parentheses that you can factor, but I can use something I like to call the giant flaming sword of the quadratic formula, because it is used to battle every quadratic, even when the quadratics are more easily factorable, or you can uh, do all sorts of completing the square, things like that to solve. Everyone still just uses quadratic formula, so we'll just do that as well. I could do completing the square with this one. It would work out really nicely, but I'll do quadratic formula. So here we go. A is 1, B is 4, and C is negative 1. So I'm going to have, when I set it up, x is equal to, I'm going to have negative b, so negative 4 plus or minus square root of b squared, 16, minus 4 times 1 times negative 1, and then all of that over 2 times 1, which is 2. Alrighty, so x is equal to negative 4 plus or minus, that's going to be 16 plus 4, so root 20 over 2. I can simplify this a little bit to make life a little bit easier. X is equal to negative 4 plus or minus 2 root 5 over 2. And now I can divide both of these terms, the two terms on top, by the 2, which will make it much simpler. So x is going to equal negative 2 plus or minus root 5. Alrighty? Now, if I look at my interval that I was supposed to be looking for a value that had a 0 slope in, it was from negative 1 to 3. Okay? Now, negative 2 minus root 5, and root 5 is, I'm just estimating, maybe 2.3, 2.2, no idea, something like that. But negative 2 minus 2 is going to be a negative 4 something, and that's going to fall outside of our interval. That would be over on this side of it. But negative 2 plus root 5 is going to give me about a positive 0.3, and positive 0.3 lies within this interval. So where is my horizontal slope? It is at x equals negative 2 plus root 5. And that is our solution. Alrighty. Hopefully that went well. We can move on to the next one. Clear the screen. Okay, so the next one is a fun one. 21 is f of x equals cosine of pi x. And we're looking at an interval from 0 to 2. Shock, shock. Alrighty. A better way to probably write this would have been cosine of x pi. So you could see that it's 0 pi, between 0 pi, 0, and 2 pi. But typically you don't do that. It's just we're used to seeing our cosine expressions as something pi. It's kind of a strange way to do this, but it works out just fine. So first off, is this continuous over that interval? Absolutely. Cosine is continuous everywhere. We don't have to worry about that. Next, is cosine of 0, like f at 0, the same as f of 2 pi? Yeah, it has to be, right? Because 0 and 2 pi, those are the same points on the unit circle. I mean, if I draw the units, worst circle ever. Oh gosh, but if I draw the unit circle, 0 is located right here and 2 pi is located right there. So they have exactly the same y value. What is that y value? What is cosine of 0 and cosine of 2 pi? It's 1 right there. because the x value is 1. So that's located at 1, 0, and the x value is always the cosine value. So that is a positive 1. They are the same value, therefore we're guaranteed by Rolle's theorem that between cosine 0 and cosine 2 pi, there is going to be at least one horizontal slope. And spoiler, we already know that's going to happen because cosine starts off up here and then does this. And assuming I can draw, there we go. So in between 0 and 2 pi, which we'll say that's what this is 2 pi, and this is 0, there is definitely a horizontal slope. Where does it occur? Well, it occurs right here. And I'm betting that we're going to find the value is at pi. Let's see if we do. So first thing I need to do is take the derivative. It starts out looking kind of strange, but it's not too bad. The derivative of cosine pi x. Well, don't let the pi part throw you off. This would be the same as cosine of 3x, for example. And since it's not cosine of plain old x, it's going to kick in the chain rule. So this is going to wind up being negative sine of pi x times the derivative of pi x, which is just plain pi. If this had been cosine of 2x, it would be negative sine of 2x times 2. So we get this expression right here, and this is, if I rewrite it, it's going to be negative pi times sine of pi x. And this is our f prime. So I need to set that equal to 0 and solve. So negative pi times sine of pi x equals 0. Well, I'm going to multiply both sides by negative 1 over pi. Why? Or divide both sides by negative pi, just so I can get rid of this. So when I do that, I'm left with sine of pi x equals 0. And this is kind of a cool question because you can think about the unit circle again. And the sine of pi x equals 0 is saying what value of sine equals 0? Where on the unit circle does sine equal 0? Well, sine equals 0. Sine is the y value. So since this is the y value, we're looking for where on the unit circle y is 0. Well, that occurs right here and right here. But I don't worry about this one because this is where my bounds are for my interval. That's at 0 pi and 2 pi right here. So this is my answer. When does sine of pi x equal 0? Well, it equals 0 when sine equals pi, which means x equals 1. And what do you know? X equals 1 lies right in the middle between 0 and 2, which is what we thought it was going to do anyways based on our little sketch. So there you have it. Rolle's theorem works again. All right, let's move to the very last one. Clear the screen. Okay, so the last one is number 42. And number 42 is using the MVT. And so the function itself, f of x, is equal to, well, we have x cubed minus 3x squared plus 9x plus 5. Okay? And we're given that the interval is between 0 and 1. So before we work this, we're supposed to use the MVT to guarantee that there's at least one solution that satisfies the MVT. So let's talk about the MVT refresh just a little bit. So MVT says I have some function, doesn't matter what it is, that's a perfectly good function for me. Let's say that I have a value here I'll call A, and a value here I'll call B. Now, there is an average slope between these two. It's the slope between the 2 points. How do I find that? Well, that's just f of b minus f of a over b minus a. Now, that gives me my average slope. Okay? What the MVT says is if the function between a and b is continuous and differentiable, then I can say guaranteed there is at least one spot, one point on the graph that has a slope that is equal to the average slope. And just looking at this, maybe that slope occurs right about there and maybe somewhere around here. 2 points in this case. Okay? So that's all the MVT says, is if the function is continuous and differentiable over some interval, the average slope between the two endpoints of the interval is matched by at least one point for the function between those 2 points. So the slope at some point between these 2 points is the same as the average slope. Okay? So we're going to start off. Let's do some calculations. We need to get the average slope first. So let's see. F at 0 is going to give me what? 0, 0, 0 plus 5, so 5. F of 1 is going to give me what? Well, 1 minus 3 is negative 2, plus 9 is 7, plus 5 is 12. Okay, so now let's get the average slope. So I'll make this the b, or this b, I should say, that's f of b. So f of b would be 12 minus f of a, 5, over b, 1, minus a, 0. That's going to give me 7 over 1, which is 7. So the MVT, since this is a polynomial, it is guaranteed to be continuous and differentiable at every single point. So the MVT guarantees there's at least one location between point A and point B that has the same average slope, the same slope as the average, which is a slope of 7. So let's see if we can figure that out. Let's go to the next page. So let me clear this. Okay. So I know I just have to remember that the average slope, first of all, let me put the function back up here then so I can differentiate it. F of x was x cubed minus 3x squared plus 9x plus 5. And then I found that the average slope was 7. Okay, so now let's take f prime. F prime of x equals, well, 3x squared minus 6x plus 9. Okay, now this is where it gets interesting. What do I set the f prime equal to that is guaranteed by the MVT? The MVT does not guarantee that there is a slope of 0. Wrong answer. What the MVT says is that there is a slope in between that has a slope matching the average slope. So what the MVT guarantees is there's a slope of 7 somewhere in this interval. Okay, so let's see if we can figure out where that is. We're going to start off, we're going to bring the 7 over, get this equal to 0, so that I can use the quadratic formula. So 3x squared minus 6x plus 2 equals 0. And so I've got my a is equal to 3, b is equal to negative 6, and c is equal to positive 2. Okay, so I get x equals negative b, so positive 6, plus or minus square root of b squared, 36, minus 4 times 3 times 2, and all of that over 2 times a, which is 6. So x is equal to 6 plus or minus 36 minus 24 is going to be 12. So root 12 over 6. I can simplify this a little bit if I do x is equal to 6 plus or minus 2 root 3 over 6. So I can divide each term by 2, which is going to give me 3 plus or minus root 3 over 3. It's slightly simpler than this form, but it's not a whole lot of difference. Only thing I gain from this really is that I know that the square root of 3 is 1.7 something. So this is approximately 1.7. So now I'm looking for x values that are either 3 plus 1.7 divided by 3 or 3 minus 1.7 divided by 3. Well, if I think back to my original interval was between 0 and 1, right? So that was a 0 and a 1. Okay. If I do 3 plus 1.7, that's going to give me 4.7 divided by 3 is going to be greater than 1. So it is 3 plus root 3 over 3 is greater than 1. So that's not our answer. Because the answer has to be between 0 and 1. But now 3 minus root 3 divided by 3. I like that one. 3 minus 1.7 would be 1.3 divided by 3 would be 0.4 something. That's approximately 0.4, and that is definitely between 0 and 1. Check. The MBT worked. It guaranteed there was at least one location that had a slope equal to the average slope, and that's it right there. So there you go. Number 42 completed. Alrighty, now we can move on to the actual section 3.3. So let me clear the screen. Okay, so 3.3 had that really long title. It was 3.3. We had increasing and decreasing functions and the first derivative test. That is a lot. So we are going to kind of ease into this. We'll take 2 lectures to go through all of 3.3 and to work tons of examples so that 3.3 is nice and solid before we move on to 3.4. Okay, so first things first, we're going to start off with a definition. So definition. Here we go. A function, a func f is, here we go, increasing, underline, increasing on an interval when for any 2 numbers x1 and x2 in the interval x1 less than x2 implies f of x1 is less than f of x2. Okay? And this actually makes a lot of sense once you break it down. So I've got some function. X1, x2. Okay? The function is increasing. It's going up. It has a positive slope. When for any 2 values, we'll call them x1, x2, that implies that f of x1 is less than f of x2. So the function f is increasing when for any two x's that where the first x is less than the second x implies that the first y is less than the second y. Okay? Now, only thing to really note about that one, and that makes sense, the y values, if the function is going up, the y values are getting larger, so the y value that is, the x value that is further away yields a y value that is higher. Makes sense. The only thing to note is that this is not an equal sign right here. It is a less than. That's because it is not increasing if it's a flat line. Oops, I changed color on you. How did I do that? That's weird. It's cool, but not what I was expecting. It is a flat line. That would be when I have my 2 points, f of x1 would equal f of x2, and that's not increasing. That is just flat. So if it is increasing, x2, f of x2 rather, has to be higher than f of x1. Okay? Alrighty, so now I can scratch this and go to the next one, which you can probably already guess what that is. And it's when you have decreasing. I'm not going to write the whole thing out, but the definition is that f is decreasing when x1 less than x2 implies that f of x1 is greater than f of x2. Well, that makes sense because if I have my two values, maybe x1 and x2, f itself is decreasing. It's going down when my f of x1 is greater than my f of x2. That makes sense. So that seems like very common sense to define something like that. Of course it's going down if the y values are going down, and of course it's going up if the y values are going up. But the main thing to take away from all this is the concept of increasing and decreasing. Those two concepts we're going to use from here on, at least for the next 3 sections. So we now have terminology we can use to describe things really, really nicely. So before we move to the next set, I want to draw something for you. I want to clear this. I'm going to draw a great big function. Well, if I don't make stray marks all over the page. Let's try this again. Great big function. Here we go. All right. That's supposed to be horizontal. All right. Now, from here to here, I'll go ahead and say that this is constant. And it's flat like that. So it means that f prime of x equals 0 right there, right? Okay, that's supposed to be flat. I swear it's supposed to be. I know I don't draw well, so just assume that I can draw that, and it's absolutely flat. It's amazing I was able to draw it so well to be that flat. So that's a place where f prime of x equals 0. Now, over on this side, we always think about it going in this direction when we're talking about whether a slope is positive or negative, right? Well, this is going down as I head from the left to the right. So this is actually decreasing. And that means that the slope of this line is going to be negative. So f prime of x is less than 0. Okay? Over on this side, I have something that's going up, so this is increasing. And that means if I look at it, it has a positive slope. So how do I denote that? F prime of x is greater than 0. So let's look at what we have here. We've got f prime of x less than 0, f prime of x equals 0, and then f prime of x greater than 0. Okay? So when you stop and think about it, there is no way to transition from a decreasing function to an increasing function without having a place where it's 0. This is the same rationale we use to find the critical numbers. We talked about how at the turnaround points, at the mins and the maxes, that exact moment has a slope of 0, and so we found the critical numbers. But what you can also say is that to the left and right of the critical numbers, you're either going to have increasing or decreasing slopes. Okay? So that is monster huge. It seems obvious, but I cannot overstate how big that is. You have your critical number value. That's where the slope is 0. To the left and right of that, the function is either increasing or decreasing. Okay? So that's it. That is going to allow us to indicate the behavior of a graph very, very, very easily. So I'm going to start back and look at a function we've done before. Our good friend, let me clear this. F of x equals x cubed minus 3/2 x squared. Remember that? That's the one that looked like this. It went like that and then did something like that. So we had this point was at 0, 0, and this point we found was at 1, negative 1/2. Okay? So in order to be able to describe the behavior of this graph completely, all I have to do is first find the critical numbers. So I will find the critical numbers first. Find critical numbers. Okay? So how do I find the critical numbers? Well, I just set the derivative equal to 0 and solve, right? This right here is a polynomial. It's continuous everywhere. I don't have to worry about any critical numbers where I have a cusp or anything like that. This is just a straight polynomial. So the derivative is going to be f prime of x equals 3x squared minus 3x. And then I set that equal to 0. So equal to 0 and solve. 3x times x minus 1 equals 0. I factor out 3x. And now I set that equal to 0, and I'll find that x equals 0 and x equals 1. Well, what do you know? It's exactly what we had up here drawn. So those are our critical numbers. So the next step, this is where it gets interesting. I hope you enjoy what we're about to do. So I've got the critical values here. Next thing I'm going to do is make a table. Okay? I'm going to make a table, and I'm going to divide it with the critical numbers. So this one is going to be, this divider is x equals 0, and this is x equals 1. Those are the two critical numbers. Now, this is where it gets fun. If you look at the graph, there are no critical numbers to the left of 0, x equals 0. The behavior of the graph goes on for infinity. It will always look something like this. It will never turn around. Why? It can't turn around because if it turned around, there would be some point less than x equals 0 at which we had another critical number. But we just found the only two turnarounds were located at x equals 0, x equals 1. So I know that the behavior of the graph is exactly the same. Once I pass x equals 0 and go to the left of that, I no matter where I look on the function, it will always have this kind of behavior. And this kind of behavior, and remember we always look at the behavior from left to right, is that I have a positive slope. Okay? So if I look at any number less than x equals 0, any number less than 0, any value of x, and plug that into my derivative, which gives me slopes, any value less than 0 that I plug into my function is going to have a positive answer. It will have a positive slope. It doesn't matter if it's x equals -1, x equals -100, x equals -10 million. Every time I plug the value in that is less than x equals 0, the slope will be positive. So the way that we're going to fill out these charts is we're going to pick test values that belong to each of these intervals, each of these sections. So I need a test value that's less than 0. I'm going to try maybe x equals -1. That is definitely less than x equals 0, so it should be fine. So now I'm going to plug that into my f prime function. So f prime of -1 equals, so this is going to give me the slope at x equals -1. Well, I can just look at this one and kind of tell. If I put a -1 in here, it becomes +1 since it's squared. So 3 times +1 is 3, minus 3 times -1. So minus 3 times -1 is +3. So 3 plus 3 is 6, but I don't care about the actual y value, or not really the y value, what the value that I get once I plug the value into my prime. All I care about is it positive or negative, because it is always going to have that behavior. If I plug in -100, well, -100 squared is 10,000. So that's 3 times 10,000 is 30,000, minus 3 times -100, which is plus 300. You can see it is a positive value because this is going to be positive because I square it and then I multiply it by a positive. And this term is going to be positive because it's a -3 times a negative value. -3 times a negative value is always positive. So positive plus positive is positive. I don't fill in the value here because I don't care what the value is. All I need to know is that the slope at a value that is less than 0 is positive. And I'm going to indicate that up here with a little line like that. Okay? Now, I need to look at what's happening in this interval. I need to a value of x that's between 0 and 1. I'm going to pick 1/2, but any value between 0 and 1 would work. So x equals 1/2. Now I plug that into my f prime of 1/2, and that is a positive 1/2, equals, well, I'm going to get 3 times 1/4 is 3/4 minus 3/2. 3/4 minus 3/2, the 3/2 is bigger, so 3/2 dominates, which means this is a negative value. Any value I put in there between 0 and 1 is going to wind up negative. Okay? So I'm going to indicate that with a little downslope. Alrighty, now move to a value. I need one that's greater than 1. Maybe x equals, I'm just going to do 10 just because I'm feeling saucy. So here we go. 3 times 10 squared is 100, so 300 minus 30 is positive, so f prime at 10 is positive. That means I'm going to put a little slant like that. Now, let's look at our expression here, what we did with this table. we're saying that before x equals 0, all the x values less than 0 have a positive slope. Then all of the values between 0 and 1 have a negative slope. All the values greater than 1 have a positive slope. Okay, now let's think about what that's saying. Between, to the left of x equals 0, the graph is going up. To the right of x equals 0, the graph is going down. What does that mean x equals 0 is? It's going up, then it's coming down. That means at x equals 0, we have a max. Then we look at the behavior at right around x equals 1. Well, to the left of it, it's going down. The slope is down. We have a negative slope. To the right of it, we have a positive slope. Down, then up, means that x equals 1 is a min. So, does that match the graph? Slope going up, slope going down, slope going up, and right there you have a max, right there you have a min. That's what this whole section is about, is can we use the first derivative test with these test values to get what the slope behavior is going to be on either side of the critical numbers. And once we do that, we're able to tell whether finally this critical number is a min or a max and this critical number is a min or a max. So that's all there is to it. And I just want to say one more time, I try not to say it for the rest of the video. I just have to say it one more time. Since there are no other critical numbers other than x equals 0 and x equals 1, we are guaranteed that the behavior does not change. So to the left of x equals 0 and to the right of x equals 1, those behaviors are set forever. The only way that they can change from a positive slope to a negative slope is if there's another critical number somewhere over here. But since we didn't find a critical number that was more than x equals 1, we know that never happens. This does not happen. So since it doesn't happen, we don't have to even worry about it. And I can put this little arrow right here and be confident that the behavior of this function never changes from this behavior. It is always heading up. All right, let's try a different problem. Let me clear the screen. Okay, so our last example is going to be f of x equals 1/2 x minus sine x. And yes, it had to be a trig function. Got to throw that trig in when we can. I will go ahead and tell you that it looks something like, if I graph this out, I'm going to have something that looks like, that. This point right here and this point right here are the only 2 points on the interval between 0 and 2 pi that we need to worry about. So we're going to see if we can find where these are. I know where they are, but I don't want to just tell you. I want to use what we've learned so far to find where these things are. Okay, so first thing I need to do is find the critical numbers. So the critical numbers occur when the derivative is equal to 0, or it doesn't exist at a cusp, something like that. But we don't have a cusp behavior. We have a polynomial, and then we have a sine function. Continuous minus continuous is still continuous. So I know this thing is continuous, and I don't have to worry about anything crazy happening with it. So I can go ahead and jump straight into finding critical numbers. So the critical numbers, so find the critical numbers. That 1, f prime of x is equal to, well, 1/2, and then the derivative of negative sine x is negative cosine x. And so now I set that equal to 0. And that gives me cosine x equals 1/2. Well, what do you know? It's another trig. So here we go. I've got to draw my unit circle. I'll try to draw a slightly better one this time. Take a little more care with it. Alrighty. So cosine is the x value for all the coordinate pairs. When does that equal 1/2? Well, that's going to occur when you had those ordered pairs where you had 1/2 √3/2, and then that they can swap position and change their signs depending on which part of pi/6 you're looking at. So it turns out that the x value is 1/2. That is when we have a short leg on the triangle, the 30, 60, 90 triangle that is given like that. So this location is at 1/2 √3/2. The cosine is the x value of 1/2. And we have that same x value down here. And down here we have positive 1/2 negative √3/2. So where do these two locations occur? Well, this one is located at 2 pi/6, which is pi/3. And this one right here, as we go all the way around, this is 6 pi/6, 7 pi/6, 8 pi/6, 9 pi/6, 10 pi/6, which is 5 pi/3. So this is 5 pi/3. Alrighty. So those are the two locations for our critical numbers. So critical numbers are located at pi/3, pi/3, and 5 pi/3. Okay? So now let's make a table. And we're going, this is step 2. This is so we can describe the full behavior of the function. And we're going to have x equals pi/3 here, and x equals 5 pi/3. Okay? So I need to figure out some test values. I need a value that is less than pi/3, so anywhere in this little arc, but don't do 0, because 0 is also 2 pi, and we don't want to use these endpoints. We want to find something between those endpoints. So I am just going to try this point right here. That point is pi/4, and so let me do x equals pi/4, because pi/4 has a really nice one. Pi/4 is √2/2 and √2/2. So the f prime of pi/4, well, f prime is 1/2 minus cosine x. So f prime, remember, this is actually f prime. It is not equal to 0. We set f prime equal to 0 to find the critical numbers, but f prime itself is 1/2 minus cosine x. So I plug in pi/4. What is pi/4? Well, pi/4, pi is 3.14. Divide that by 4, and you've got like 0.7 something something. So 1/2 minus 0.7 something, that's going to be a negative value. So this is negative. And I'm just going to indicate that with a little thing right here going down. Alrighty, now I need a test value between pi/3 and 5 pi/3. That one's easy. So between this and this, I'm going straight for pi. That's a nice, easy one to figure out. So x equals pi is going to be our test value. F prime at pi, what do we get? Well, we get 1/2 minus cosine of pi. What is the cosine value? Well, it's the x value, and at pi, that's -1. So 1/2 minus -1 is 1/2 plus 1, which is positive. Again, I don't care what the actual value is, just what sign it is. So SIGN, sign. So it's positive, which means I'm going to indicate that little upward slope. Finally, I need a value that is greater than 5 pi over 3, but not 2 pi. So I'm going to choose right there at 7 pi over 4. So it's 7 pi over 4. X equals 7 pi over 4. F prime of 7 pi over 4 is going to give me, well, let's see. I'm going at 7 pi over 4. The x value is still 0.7. So 1/2 minus 0.7 is negative. And so we get a negative there and it heads down. Alrighty? So I have for my function up here that we have a horizontal slope at x equals pi over 3 and x equals 5 pi over 3, which is what we expect to see because we have those two turnaround points there. We also have that before x equals pi over 3, the behavior of the graph is going down. And so left of it is going down, to the right of it it's going up. What does that make the location right there? It makes this location a max. No, down. That was bad. Hold on, let me just redo that. You didn't see anything. That makes sense. It's going down, then heading back up. That makes that a min. Now, for the second critical number, it's heading up and it's going down. That makes that an actual max. And what do you know? It matches our function exactly. So there you have it. By doing the finding the critical numbers, step 1, then making this table and plugging in our test values that fit these intervals, we're able to tell what the behavior is of the function to either side, if it's increasing or decreasing, and then we're able to actually tell what the critical numbers are. Are they mins or are they maxes? Okay? Whew. So with that in mind, that's all we're going to do for today. Your homework is going to be from section 3.3. It's going to be 19, 23, and 43. 19, 23 are nice polynomials. 43 is a trig function. So have fun with it, and I will see you next time. Take care.